Right, we're going to look at 3 different algebraic proofs, and all of these 3 proofs are going to be to do with the sum of certain types of numbers. So the first one we're going to look at is this one here, and that is that we're looking at proving that the sum of 3 consecutive integers is a multiple of 3. So firstly, we need to think about what the 3 consecutive integers are and then find the sum of these integers. The obvious place to start with this would be to use n as the first integer. If n is the first integer, then the other 2 integers are going to be the 2 numbers that come after that. If n is the first number, then n plus 1 is going to be the number that comes after that, and then n plus 2 is going to be the number that comes after that. And if we're looking at finding the sum of those integers, then we're going to be adding those together. Now, it doesn't really make a difference, but quite often when you're working out things like this, then we'll put brackets around those 2 just to recognise that these represent the 3 different integers that we're talking about here. So we're looking at trying to find the sum of those integers. So the first thing we're going to do is we're going to add and collect these terms together. So we've got n, add n, which is going to give us 3n, and then we've got 1, add 2, which is going to give us 3. So just by simplifying and collecting the terms there, it's going to give us that expression 3n plus 3. We're now trying to prove that this is a multiple of 3. And the way that we can often do that is by proving that 3 is a factor. If 3 is a factor, then that proves that it must be a multiple of 3. How do we prove that 3 is a factor of an expression? Well, we can factorise that number out. If we can factorise that number out, then that shows that 3 is a factor. So we're going to look at factorising 3 out of this expression, and if we're going to do that, we're going to write 3 in front of the bracket. What times us by 3 to give 3n would be n. What times us by 3 to give 3 would be 1. So we are left with that bracket there. So 3 bracket n plus 1. So this proves that 3 is a factor. So all I'm going to do now is just write a conclusion to state that this proves that this is a multiple of 3. So I'm going to write that 3 is a factor, therefore 3n plus 3, which is the expression we had here, we'll say is a multiple of 3. So because 3 is a factor, this must be a multiple of 3. And if that's a multiple of 3, we're saying that the sum of these 3 consecutive integers must be a multiple of 3. Okay? So that's how we've shown that that is therefore a multiple of 3. The next example we're going to look at is this one here. And this says, or has asked us to prove that the sum of any 2 even numbers is always even. Now this is something that's really obvious to us. If we're adding together 2 even numbers, we know that our answer is always going to be even no matter what number we choose. But this is something we can also prove algebraically. This says prove that the sum of any 2 even numbers is always even. So it actually doesn't matter here which even numbers we choose to use. We could choose any. I'm going to just write out what all the even numbers would be, just to give us an idea here of which we could use, and then we'll choose any 2 of them and we should still get the same outcome. So we should hopefully know that 2n represents an even number. And 2n represents an even number because 2 is a factor. Okay, any even number must be a multiple of 2. So 2 lots of something will always give an even number. Now, if that gives us an even number, if we then think about the next even number along, that's 2 after that even number. So if 2n is the first even number, then 2n plus 2 would give us the second even number. And 2n plus 4 will give us the third even number, and 2n plus 6 will give us the fourth even number. And we could substitute in a value of n, and if we did that to each of those, then we should get 4 consecutive even numbers. So if n was 1, we would get 2 times 1 is 2, 2 times 1 plus 2 is 4, 2 times 1 plus 4 is 6, and 2 times 1 plus 6 is 8. So 2, 4, 6, 8. So the first 4 consecutive even numbers. Now this says prove that the sum of any 2 even numbers is always even. So here it doesn't actually matter which 2 we choose. We could make life really easy for ourselves and just add together 2n twice. because it says any two even numbers. We could choose 2n and 2n plus 2. We could choose 2n and 2n plus 4. It doesn't matter. Any two even numbers. For this, I'm going to choose the first two even numbers here, the first two consecutive even numbers. So we're going to add together 2n, and we're going to add together 2n plus 2. And if I add those two together, then we're going to get 4n plus 2. Now we're trying to prove that this is even. And if we're trying to prove that something's always even, we're trying to prove that 2 is a factor. And to prove that 2 is a factor, we're going to factorise 2 out of this expression. So I can factorise 2 out of this expression by writing 2 outside the bracket. 2 times what is 4n? That will be 2n. 2 times what gives 2 will be 1. So that is the bracket we're left with. So because we've successfully factorised 2 outside, that has shown that this is a factor of 2 and therefore an even number. So I'm going to write that 2 is a factor, therefore 4n plus 2, the expression that we had here, is even. So we have shown that the sum of any two even numbers here is going to give us an even number. And we get the same outcome here, no matter which two of these even numbers we've chosen to add together. And the third and final one that we're going to look at is to prove that the sum of 5 consecutive odd integers is a multiple of 5. So 5 consecutive odd integers. So now we need to think about what an odd integer is. We need to know that if 2n represents an even integer, then an odd integer will always follow an even integer. So if an odd integer is always one after an even integer, if 2n represented an even integer, then 2n plus 1 would represent the number after that. Okay, so 2n plus 1 will always represent an odd integer. 2n take away 1 would also do the same thing, because that would be looking at the number before an even number, which would also be odd. So sometimes people would use 2n take away 1, sometimes people would use 2n plus 1. Both of those would work. Let's say we're going to use this as our first odd integer. If we're looking at the sum of 5 consecutive odd integers, then we need to write out the 4 odd integers that come after this. So what's the next odd integer? Well, that's going to be 2 after this. And if we're adding 2 to the number we've got there, that would give us 2n plus 3, because that's going to be 2 after this one here. 2n plus 2 would be the one in between, and we're not including that because that would be even. So that would be the next one. The next one we'd find by adding 2 again, so 2n plus 5. The next one we'd find by adding on 2 again, which would be 2n plus 7. And the next one we'd get by adding 2 again, which would give us 2n plus 9. So those are the first 5 consecutive odd integers. We're trying to prove that the sum of those 5 consecutive odd integers is a multiple of 5. So we now need to add these 5 together. So my next line, I'm going to add those 5 integers, and I'm going to write those in brackets just so we know that in each of these cases, each of them represents a different odd integer. Right, so if we want to now add these together, let's look at the n's first. We've got 2n plus 2n plus 2n plus 2n plus 2n, which is going to give us 10n. And then if we add together the numbers we've got here, we've got 1, add 3, add 5, add 7, add 9, which is going to give us 25. So we're left with the expression 10n plus 25. Now we're trying to prove that this is a multiple of 5. And if we're trying to prove that something's a multiple of 5, then we want to show that 5 is a factor. How can I show that 5 is a factor of this? I can factorise 5 out. So let's see if we can factorise 5 out of this. 5 times what gives 10n, that will be 2n. 5 times what gives 25, that will be 5. So we've successfully factorised 5 outside of that bracket, showing that this is a multiple of 5. So let's just write a concluding statement. 5 is a factor, therefore 10n plus 25, that's the expression that we were factorising here. That was the sum of all the 5 consecutive odd integers. So 5 is a factor, therefore 10n plus 25 is a multiple of 5. So we've shown that if we find the sum of any 5 consecutive odd integers, it will always give an answer that is a multiple of 5. So just bear in mind that with these 3 examples, we always looked at the sum of certain integers, and then we were either proving that they were odd or even or a multiple of something.